free. And let's just go over what's happening here. There's a library called Squarify. I've actually never seen this one before, but it was collected and installed. And we have Seaborn, PyPlot, NumPy, Pandas, RGB2Hex. You've seen all these, CM, PX, Graph Object, Squarify, importing, initializing notebook, a word cloud, SciPy, pill imports inner image, and then we have sklearn libraries for standard scalar, multi-label binarizer, k-means, and then label encoder, and then we have CMAP2, and then basically the color stuff in a range. We're loading this data. It's a marketing campaign CSV file, looking for missing values, and then how many values have a sum of those, doing some feature engineering, kind of replacing some of the values that we have here, replacing marital values and grouping them. So education group, marital status group, kids are grouped, looking at different campaigns, purchasing, and then printing out all the data types and the size of the table. And then we have the removing outliers. It's removing income and dropping columns, and then remove all the unnecessary columns, label and code the data, education and marital status column, and then basically just go from there, do some standard scaling. And we have an optimum number of clusters that we're trying to define here with k-means clustering with random state and k-means plus, and it's trying to fit it on. And the k-means clustering method, how does it work? It divides k-means into a certain number of clusters of k, finding the centroid of the current partition, calculating the distance of each point to the centroid, grouping based on the minimum distance. After regrouping, reallocating the points, you find the new centroid of the new cluster. So you usually have 4 clusters and you fit them, and then you do a prediction, and then it's using the cluster number, and then you make a plot. It's giving, we can see there's blue, red, and then this teal type of color. I think there's a third cluster, a fourth cluster in here somewhere, but I don't see one. Maybe it's these like little outlier points. And then it's telling us like the values on each of the clusters and how many counts they have. So it looks like this third cluster just has 21 values. And it's telling us the total amount of spending or purchasing for each of the clusters and their income. This one's doing for 5 clusters and making a prediction on it. Again, it's giving us the values starting with 0 to 4, so there's 5, and then that's kind of what we have for clustering. Linear regression is the next thing we're going to be talking about. It's used to model relationship between 2 variables by fitting a linear equation to given data where one variable is the explanatory variable and the other is the dependent variable. And we have a ggplot. You load the data. Again, it's data31.txt, so it looks like there's population and profit. And you make a visualization of profit versus population. You calculate cost, and there's a cost function here. The objective of the linear regression is to minimize the cost function. So you define the cost function as xy with data. There's a length of y, make a prediction with data. There's an error, you square it. I'm not really sure how they got this calculation, but it seems right. You have the data population values with the size, append the data with NumPy and reshape it, and then look for the data with profit, and then give data a certain value and have a cost function. This is what I implemented. Gradient descent is pretty important. It helps to minimize the cost function by updating the below equation and repeating until convergence when it comes together. So we have x, y, theta, alpha, and iterations. Cost is put into a list. There's a loop for every value in the range of the iterations. Look at the x dot for the y prediction and have a numpy dot with the transposed for the error. This is the theta value. Subtract alpha times 1 over m times error. M was probably defined above somewhere. Append this cost, then return theta and the cost, and then have this for the gradient descent. That's the equation we got. Visualize this cost function with theta 0 and theta 1 have cost values. Again, there's a loop. Don't know what surf is, but it's plotting theta 0 and theta 1. So this is what the gradient descent looks like in 3D space. And you plot the convergence as converging down with a certain number of iterations. Then you have training data with the univariate linear regression fit. So you squeeze the theta, you have this population and profit, x and y values, and then you have this linear regression fit graph over here. And then I guess the next thing we're going to go to here is multiple linear regression. So linear regression is used to model a relationship between two variables by fitting a linear equation to given data where one variable is explanatory, the other is a dependent variable. Multiple linear regression uses many explanatory variables to predict the outcome of a target variable, two or more independent variables and one dependent variable. So you have pandas, numpy, seaborn, sci-bi with the skew value, percent matplotlib inline, and then you have this RC parameters plot. Load the data. This is data 32 CSV, which is TV, radio, newspaper, and sales. Find relationships between the features and the target with the pair plot, and then have a linear model to import linear regression and fit those values, and then find the intercept and the coefficient. Have a heat map, do feature selection, import R squared, have L2 as linear regression fit for TV and radio. L2 predictions uses the X value with TV and radio, and then print the R squared score. Then we have another linear regression with TV, radio, and newspaper, 3 variables, so it's more multi-linear regression. Have a prediction on those 3 variables and print the R score, and they're pretty much the same, so not much difference. Evaluation using train, test, split, and model metrics. We have mean absolute errors, the mean of the absolute value of the errors, mean squared errors, the mean of the squared errors, root mean squared errors, the mean of the squares. Then we have this model selection with train, test, split, metrics with mean squared error. We have our add sales, train, test, data, linear regression data. We have predictions, and then we have this RMSE score here. And then we have add sales and linear regression and predictions. And then this is kind of what we get for RMSE and R squared. I don't know what yellow brick regressor is, but it's importing prediction error and a residuals plot. And then you do that prediction error with the fit, and you have this kind of plot that's shown. And that's everything for today. Thanks for listening.